today we are going to continue talking about electrostatic sensing. Oh, sorry.
Before that, we have doubts in the assignment. Can we talk about that?
Sure. What are your questions? You're asking about the homework assignments?
Yeah.
Sure.
The third one, the springs.
Open. MSE 402. Which problem?
Yeah, the first one.
The first one. Which of the springs is softer? Okay, so what we have here are, let me write this down. So this bit right here is fixed, as is this bit. So we're assuming we have no bending there. And since this bit right here is small, let's consider this whole thing fixed as well. So we have a guided beam part over here and a guided beam part over there. Assuming we have everything that's thicker, let me pull out my notes for springs here so I can remember how this stuff works because I haven't thought about it in a couple of weeks. Beam. So this section right here is going to have a spring constant KGB. Let's just call it 1. That is going to be 12 times the Young's modulus of the material, whatever it is, times I, the moment of inertia, which is dependent effectively on the dimensions of the cross-sectional area. So it's going to be whatever it happens to be, divided by the length here. So 100 microns cubed, right? And because we have those two in series, K for spring 1 is going to be 12 EI over 100 microns cubed. All of this times a factor of 1/2, which is going to look like 6 EI over 100 microns cubed. Anything seem suspicious or incorrect there?
So the right one will be parallel form.
Right. So over here, we also have a guided beam thing. So we're considering this part to be fixed, this part to be fixed, and then we have a guided beam bit there and a guided beam bit there. And let's call this KGB2. Oops, sorry, hold on. this one piece is gonna have 12 EI over this length of 200 cubed. Right? And then there are two of them in parallel. Right, so K2 is gonna be 2 times 12 EI over 200 microns cubed, or 24 EI over 200 microns cubed. And so now we need to compare these two things, right? So let's just say, yeah, so we're gonna have 1 over 100 microns cubed compared to 4 over 200 microns cubed. Which one is going to be greater than the other? Right, because whichever one is greater is the stiffer of the two springs. Right, so that seems legit.
For the second question, just one doubt, like I have tried all the combinations for the guided beam, but it's like which length to consider till I'm like, do we have a combination of the length or only one length?
So why is this picture looking, does this isn't how it looks for you guys, right? Okay, so let me zoom back out. All right, so effectively for this one, between here and here, we have one guided beam spring. Between here and here, we have a second guided beam spring, and those are connected in series. Right? And then there are 4 of those connected in parallel, giving us the total spring constant of the system. That seem legit? That's how I'm looking at it anyway, as an electrical engineer. That's how I see it. So.
Do you have any other more problems on like guided beam for our reference, like with the solution we can do by our own?
I mean, I can try to find some, like I just made these up. But yeah, so that's how I would consider this as, I'm considering it a guided beam because I know that this is an anchor point for sure. And I'm considering that this piece is so small effectively that it's not going to easily extend or bend. So whenever I'm thinking of beams as springs, I'm looking for long stretches of things. And in this case, because they have different dimensions, I consider them 2 different guided beam springs connected in series. Where, again, making the assumption that this part right here isn't allowed to extend or rotate or bend. And then, anything else?
For the assignment call, problem 2, because RMS 1.024. That's those for our
Homework 4, let's look. It's been 2 weeks since I've thought about things. So you said problem 4?
No, problem 2.
Problem 2. All right, so let me think about this here. All right, so we have an AFM system. We have a mass of 25 nanograms, a mechanical resonant frequency of 20 kilohertz, and we want our noise displacement. Okay. So
hard, very far away. So instead of it being in Armstrong, last time still far minus not still times still far.
Oh, I mean, there's always a possibility. I just made a simple mistake here. I would have to look at I solved it using MathCAD here. I'm trying to think, so I probably like what I did here.
That can be the case, so like I'm also getting different answers from you.
Yeah, that's always a possibility. There's always a possibility that I have made a mistake because this is my first time doing this in several years. So that's what I'm just trying to remember what I did here. So the resonant frequency omega naught is going to be 2 pi times the linear resonant frequency. And this is going to be equal to the square root of K over M, right? Or is it M over K? One more. So this would have been for the accelerometers stuff, I believe, right? K over M. Okay. So guys, trying to figure out why my laptop isn't charged yet. There we go. So accelerometers got to get better organized. That's RMS velocity. That's not useful here. Yeah, so I'm trying to figure out what the heck I did with my notes for noise.
I have it right after time domain.
I mean, I don't,
That's useful.
so I'm trying to, so from what we have here, we should be able to solve for the spring constant of the system, right? You know what, let me just look at my damn solution. And see what I did. Problem 2, right? Let's see if I have the right version of MathCAD installed on this computer. Okay, so I said that no, that's definitely problem 1. Maybe I just saved it as the wrong thing. Let's look at what I have saved for problem 1. Open new file. I'm getting frustrated. All right. So I'm trying to think from based on the information that I have here and not having my notes for mechanical noise, because we're trying to find RMS noise displacement. So we want X RMS. That's stuff for a different class.
The equation for RMS to be give us X RMS to be root of KBT divided by 2.
Okay,
So divided by n, rather. So.
Yeah, it's yeah.
Okay, it's good.
Yeah.
Yeah, KB times T divided by K.
okay. So that's your RMS displacement, KBT over K. And then K is going to be, let's see, M omega naught squared. Now it opened up. So that's problem 3. Yeah, for whatever reason, I guess I just didn't save 2 when I did it, so. There's my keyboard. Let's throw this crap into math. All right, so we were given M is what value? So 25 times 10 to the minus 9 grams. What other pieces of information were we given? F naught is 20 kilohertz. Don't need any of that junk. So omega naught is equal to 2 pi times F naught. So that seems legit. Our spring constant K is equal to M times omega naught squared. So this, let me just double check that this is equal to newtons per meter for a linear spring. Yeah, 0.95. And then X RMS is equal to the square root of KB times T over K. 1.024 times 10 to the minus 10. So that's 1.024 angstroms, which is what I got. So take a picture because that's the solution. By the way, you guys, as students of Louisiana Tech University, all have access to this program for free if you want to use it for things. Because I prefer it than using calculators. So that's me.
I still have it from, was it freshman year or something?
Yeah, all the students who are here as undergrads and all this kind of stuff, they literally got introduced to this as freshmen. I like this particular program because it takes into account units and all that kind of stuff. But it gives it to you in SI units. So like, for instance, when I got to this step, it gave it to me in kilograms per second squared. And I was like, wait a minute, is that the same conversion as a Newton per meter? And it is, but it'll take those into account. Like you can literally go in and tell it that I want it, the units to be in newtons per meter. just to make sure everything's on the up and up, and we'll take care of it for you. It doesn't do femtofarads for some reason, which will be a thing. So like I usually have to do 10 to the minus 15 farads, but it does do picofarads. So anyway, so I let me save this. That's problem 2 solution.
I remember from the power systems class, it had Hartman with RPM and radians per second.
So radians per second is the same thing as a hertz, because a radian is a dimensionless quantity. So that's why right here, I'm perfectly okay with this saying omega naught is in per seconds, because I understand that a radian is inherently a dimensionless quantity. So whenever I see it in per seconds, I use that for radians per seconds for angular frequencies. But whenever I write a linear frequency, I always tell it to give it to me in hertz so that I can mentally differentiate between the two things, even though according to MathCAD, dimensionally, they're identical. Anyway, so all of that to say, there's always a possibility that I've made a jackass mistake. Anybody who's had me for classes before knows that is very much on the table. So if I put an answer down and that says that this is the correct answer, and you're like, I don't think that's right, by all means ask and let's figure it out. Okay. I would consider the answers that I provide to you as more of a first pass guesstimate based on me hurriedly getting a solution to make sure, like, that's largely me making sure I provided you enough information to solve the problem. And then whether or not I did it correctly is an entirely different question. So, yeah. And then as I teach this class more and more, the kinks will get worked out. So you guys are guinea pigs. All right. Any other questions regarding the homework problems? Stephen?
Just kind of a dumb one, but a quick one on the units for problem 2 and homework 2. Problem 2 and 3 for part C, the spring constant is in units of newtons times meters. I know that's the case when we're talking about
Rotation. Yeah, but it should be newtons per meter.
Right. That's why I was just checking to make sure I wasn't.
No, so did I just write something down wrong?
Yeah,
It's multiplying instead of.
Okay.
It's Newton meters instead of.
Yeah, so for homework 2, you're just asking about the answers for problem. For C, let's see, so C is. Well, sure. Okay, but yeah, so C should definitely be newtons per meter. D should be Newton times meters. Because that's a rotational, yeah. Yep, so that's on me. Any other?
But like we can have more questions with the guided list that will be.
Okay, we'll try to find some. Yeah.
If you're asking that in the exam, then.
I don't know what I'm asking in the exam. I don't even remember when I said it is or anything like that, but I'll try to scrounge up some other problems and all that kind of stuff. I won't commit to it purely because I consider this class a new prep, and I also have another class that I'm preparing everything like from scratch for, and it takes a lot of time to do that, in addition to the 2 other classes that I'm teaching. So not trying to be a jerk, but my time is limited, so I will help you out as best as I possibly can, but you got to work with me too.
You're just kind of talking about the exams. On the syllabus, it says that's supposed to be the 13th, basically a week from this coming Friday. Are we still planning on that, or is it going to be further out?
I think it's going to be further out.
Okay.
My best guess is it's going to be further
I
out.
think what we discussed.
I want to cover-
Like 2 weeks from today.
I want to cover all of the sensing before we have our exam, and then give you guys a class meeting or so to, like, you know, yeah, exactly right. Like, not like you learn a thing and then immediately you're tested on it. At least give you one more class period to be like, hey, let me ask questions about this as I'm working on the homework stuff. So today, we're half an hour in and haven't started on what I wanted to talk about. So today we're going to finish capacitive sensing. Friday, we're going to do piezo-resistive sensing. Monday will be piezoelectric sensing. Then I think next Wednesday will be thermal sensing. Friday will be our data process things. The Monday after that is MLK. So probably the Wednesday after the MLK break will be the actual date of our first exam. That's my best guesstimate based on the pace that we are currently setting. So I think that is the 19th, no, the 18th. Yeah, the 18th. So 2 weeks from today, instead of 2 weeks from.
Or a week from Friday.
Right, yeah. So 2 weeks from today would be my best guess as to when exam 1 is actually going to be held. All right, anything else, or can I talk about what I'm supposed to talk about today? All right, close all this crap down. Discard. Stephen, would you mind sending me, unless you've already done so and then I'm just a jerk and ignored it, send me an email regarding that typo on the thing?
I hadn't said how.
Okay, I'm just always a possibility. I'm a jerk and just didn't answer things as well. So. All right. Piecing together two things here. Okay. Electrostatic sensing. Part 2. Capacitive comb drives. So when we last talked about electrostatic sensing, we pretty much limited our analysis to large plates, okay? Capacitive cone drives are also effectively just parallel plate capacitors, but they're a little bit more fancy. So I'm going to draw a structure here. That vehicle is very loud. So this is going to take me a minute or so to draw. So just giving you guys a heads up.
Hey, Dr. Hartman, you stopped screen sharing.
Oh, that looks terrible. Sorry about Zoom dying. I'm getting things going again. All right, so we have this here structure, not quite done yet. So we have a series of fingers like so, and then we're also going to have in between these guys. And let's say that these fingers on bottom are fixed. And this whole structure at the top is movable. Okay. And depending on what direction it moves, we have different things. Okay, so let's talk our way through this briefly with some critical dimensions here. Okay. So our first dimension of importance, let me do this in a different color, because if everything's in black, it's going to be even more confusing. So we have some separation between these interdigitated fingers, which I'm going to call D naught. And let's say that when our system is at rest, our fixed fingers are directly in the middle of the gaps of our movable fingers, like so. There is also this dimension, which I'm going to call D sub F. We'll talk about that in a moment. Okay. We have this length, which I'm going to call L naught, which represents how much the fingers are overlapping each other. And then we have this distance T naught, that is the thickness of the fingers, where we're assuming that the fixed fingers and the movable fingers have the exact same thickness. Okay. So this structure is composed of interdigitated fingers, more commonly called a comb drive, because it resembles a comb like you would use to comb your hair, because engineers are lazy. Okay. And we have multiple different capacitances that are formed by this structure. Okay. So for instance, there is a sidewall capacitance that formed between the fixed finger and the sidewall of the movable finger to the left. So I'm going to call this CSL, or C capacitance. S is for sidewall and L is for left. Similarly, we're going to have a capacitance here, CSR, between our right sidewall of our fixed finger and the sidewall of the finger to movable finger to the right. And then we also have a capacitance here that is a fringe capacitance. Okay. So we're going to talk a little bit about this fringe capacitance later on. Effectively, it is a parasitic or largely unwatered capacitance. It is very difficult to get a closed form solution for the value of this capacitance, because our parallel plate capacitor equation is really only valid for infinitely large plates, right? Where we're neglecting some fringing capacitance. Since this fringe capacitance CF is formed by effectively a very small area overlapping something far away, our parallel plate capacitor equation isn't particularly valid there. So we would have to do something like finite element analysis or something like that, like computer simulations, in order to figure out what that fringe capacitance is. For our derivation here, we are going to assume that that distance df is large, such that that fringe capacitance is small. If the area of overlap is small and the distance is large, that fringe capacitance should be small compared to our designed capacitances. So it exists. We are going to neglect it. Neil. So, I mean, there's going to be some voltage associated at the fixed nodes, and there's going to be some other voltage at the movable nodes. We're just saying effectively, from the perspective of there are two conductors near each other, we have capacitances. Okay. All right. All right. So this is a very interesting design, because effectively it can work as a capacitive sensor in a multitude of different ways. Okay. So we are going to consider 3 different cases. Technically, there's a 4th case, but I'm not going to talk about it because the math behind it is annoying. So let's talk about case number 1. where we have transverse movement, okay? So I'm going to redraw this thing, but from a top-down perspective, pretty simplistic view here, okay? This will be enough. All right. And then I'm going to draw my fingers here, and I'm intentionally not drawing these fingers directly in the middle. Okay. So our axis of motion will be from left to right. We have some length of overlap L naught. And then here, we have some distance D naught, which is our rest position, plus X. So our movable system has moved with respect to our fixed system, such that we have a large distance between our stationary finger and the finger to the right. And then we have a small distance here. This one will be D naught minus X, like so. And then we have a thickness direction into the page. So just for the sake of argument, we're going to call this the Y direction, this the X direction, and our Z direction will be out of the page, okay? So for an individual finger, the capacitance CSL will be given by epsilon times the area over the distance. That is our generic parallel plate capacitor formula, right? So assuming that there is an air gap, this will be epsilon naught. Our area is the length L naught multiplied by the thickness T naught divided by the distance separating our fingers, right? Where in this case, this distance is D naught minus X. Similarly, CSR will be epsilon A over D. And so this is going to look like epsilon naught, L naught, T naught over D naught plus X. Our total capacitance is going to be N times CSL, plus CSR, because the number of fingers is going to increase our overall capacitance, because these are going to be effectively connected directly in parallel with each other, right? So if our movable structure is at one potential and all of our anchored fingers are at a different potential, all of those capacitors formed are connected electrically in parallel with each other, right? And so this gives us an overall capacitance of N epsilon naught, L naught, T naught times a factor of 1 over D naught plus X plus 1 over D naught minus X. And we can also define what's called a sensitivity. So this is going to be the change in capacitance with respect to the change in displacement. And I'm not going to force you guys to do the derivative. It's going to be 1 over P naught minus X quantity squared, and then we have a minus sign here, 1 over P naught plus X quantity squared. Okay, so from this thing here, we can actually see a couple of advantages that we might have by using this type of structure over a simple plate moving into or out of the axis. This is a surface micro machine process inherently, which means it's largely compatible with CMOS processes. Okay, we're just doing everything on top of an already established wafer, so we can easily integrate other circuitry with a structure like this. We have a very good control over what the capacitances are because we can ramp them up or scale them down just by adding more and more fingers. Okay, so mismatches in alignment are going to have a much smaller effect on a structure like this than they would on a single large plate. For this particular configuration, there is a nonlinear relationship between the total capacitance and the movement of the frame, or the movement of the proof mass effectively. And so what I mean by that is if the quantity X is very small in comparison to the quantity D naught, the change in capacitance is very, very small. If we, I believe I did the math, and if X is about 10% of D naught, the change in capacitance is 1%. So not particularly large, so not particularly easy to measure. That being said, if the change in displacement is about 50% of D naught, the change in capacitance is about 33%. So that's significantly large. If the change in the change in displacement is about 70% of your initial gap, the change in capacitance is about 100%, meaning it doubles. And anything larger than that causes it to exponentially increase. Now, there are some limitations to this that we're going to talk about more when we get into electrostatic sensing and effects like pull-in and stiction, but we can get very large change in capacitances if we can get large-ish changes in displacement on the order of D naught or half of D naught or so. We can see very, very large changes, but we do have a nonlinear relationship between those changes, okay? I have an example problem, but I'm not going to do it because we don't have enough time to cover everything. So I might just upload these notes for you guys. So this is our first case. So effectively, we have a situation to where we have our fingers interdigitated like this, and then we're moving back and forth like so, and changing the distance of the air gap. Very similar to what we did or what we saw previously. Now let's talk about how we can actually do area tuning with a system, okay? So our second case is going to be lateral movement. So we have our exact same structure. like so. And now let's say that our fingers are directly in the middle. Like so, so that we had, if this was our dimension L naught, we now have some small change here, y. So we've changed the distance by which our fingers are moved into the gaps. These distances are now d naught. And for our coordinate system, here's the y direction. Z direction is out of the page, X direction is to the right, and our axis of motion is like so. Okay. So we still are going to have some sidewall capacitance CSL and some sidewall capacitance CSR, but now instead of changing due to a change in the D dimension, we're having an effective change in the area, right? So in this case, CSL and CSR are going to be the exact same thing. And that is going to be epsilon A over D, which is going to look like epsilon naught. Since our length dimension is the one that's changing, this is going to look like L naught minus Y times T naught over our gap D naught. And so our total capacitance is going to be twice N times any of those single capacitances. And we will have some sensitivity to a displacement in the y direction. Since this is this is going to be the derivative of C total with respect to y. And this is a simple linear relationship, right? So this is going to be 2n E naught, or excuse me, epsilon naught T naught over D naught. So that means effectively that if we change the overlap, so if our displacement is, let's say, 20% of the length L naught, our change in capacitance is 20%. We don't really have to do a whole heck of a lot of figuring things out. That simple linear relationship means that we get 1-to-1 tuning ratio there. So that is lateral movement. So what do you think is our other option? So rotational is the one that we're not going to do because it's a pain in the butt.
Along the z-axis.
Exactly right. Movement along the z-axis, because that is also going to cause a change in the area. Yeah.
So we're just gonna change Y to Z.
Pretty similarly, yep. Nope. So our third case is going to be vertical movement. So let's say that this is our stationary finger. And this is our movable finger, so let's write that down. Stationary, movable. Establish our coordinate system. So this is the z-axis. This is the y-axis. This is the x-axis. Um, our distance L naught is constant, our distance D naught is constant. And this was T naught. And this changes Z. So once again, we should observe that CSL will be equal to CSR. And this is going to be epsilon naught, L naught, T naught minus Z, excuse me, divided by D naught. Our total capacitance is then 2N times epsilon naught, L naught, T naught minus Z over D naught, and our displacement sensitivity is the derivative in the total capacitance by the displacement in the Z direction. And this is going to be a simple number effectively over D naught. Really, this should have a minus sign and the other one should as well, but why can't Z be a negative number, right? Why can't they? Actually, I take that back. This one has to be negative by definition. Because you can't, it's impossible to increase the area of overlap between the plates if the plates are the same thickness. It can either be fully overlapped or not. And if it's not fully overlapped, then obviously the change in capacitance is going to be a decrease in capacitance. So, and then as Sam pointed out, there's technically a fourth option, which would be a torsional thing. So that is also going to be an area change, but mathematically describing that as a huge pain in the butt. So I'm not going to do it. But effectively, if you have two plates, if they start out like this, the area of overlap is large, and then as one rotates out of plane with the other one, the area of overlap changes significantly, so that you can get a very, very large change in capacitance, but mathematically describing that is very, very difficult because it's not a one-dimensional change, it's a two-dimensional change. So, yeah, so I'm not going to try to mathematically describe it. These three are good. So what's really interesting about this, this is the type of capacitance that is used in analog devices, accelerometers, which really started off the surface micro machining wave of processing. And what's so fantastic about this is because you can actually make a 3D accelerometer using the exact same structure. You just have to use your support springs in different dimensions to allow movement predominantly in the X direction, predominantly in the Y direction, and predominantly in the Z direction. So you would replicate the microstructures exactly. It's the springs that change whether you want X-axis movement, Y-axis movement, or Z-axis movement. And then you wire all three of those things together, and you can see relative changes in the X, the Y, and the Z dimensions. So you don't want your structure moving in all three directions. That's a nightmare. You want three structures moving in only one direction each to allow you 3-axis acceleration movement. So that is what I wanted to talk about today. We could talk very briefly about parasitic capacitance, kind of as a conceptual thing here. Yeah, let's do that real quick. So please remind me, did we talk about ratiometric capacitance measurement before the break? Particularly like a Wheatstone bridge kind of thing?
Yes.
Right, okay. So, yeah. So let's say that we have a Wheatstone bridge configuration. Like so, where we have a reference capacitor here. A reference capacitor here. This is our voltage V1. And then we have something over here. Like so. So this is a capacitance. Let's call this our work capacitance CW2. That is C naught plus delta C. And this is our work capacitance CW1. That is going to be C naught minus delta C. There's our ground. And over here is our voltage V2. This is our input voltage V, and I believe we found out that our output voltage, which is defined as V2 minus V1, is just going to be delta C over 2 T naught, if I'm not mistaken. So what if we had parasitic capacitances, like our fringe capacitance and things like that? How is that going to influence things? Let's say that we are able to effectively shield and ground our fringe capacitance such that there's going to be some capacitance CP here between where we're measuring our voltage V1 and ground, and here where we're measuring our voltage V2 and ground. How does this change the output of our system, right? Yeah, the V at the top. Yeah, I forgot that. Yeah, nope, that's fair. Absolutely fair. So in this case, V1 is going to be V times, so we're going to have C naught plus CP divided by 2 C naught plus CP, just using voltage division. V2 is going to be C naught minus delta C plus CP. Let me put my V out front before I forget it again. Then I'm going to have C naught plus delta C plus C naught minus delta C, so it looks like twice C naught plus CP again. And from this, V out, V2 minus V1 is going to look like V times, in this case, minus delta C over 2 C naught plus CP. And I could have made that a plus sign by putting my work capacitance at the top, have a minus sign and all that kind of stuff. The sign isn't particularly important there. The effect of the parasitic capacitance is. So what is the parasitic capacitance doing here? It's making the denominator larger, which is making the relative change in capacitance effectively smaller. So it's decreasing our sensitivity. So the presence of parasitic capacitance is one of the biggest drawbacks of electrostatic or capacitive sensing, because effectively any two electrical conductors form a capacitance. How do we make these capacitances smaller? Well, the simple answer is we make sure that their area of overlap is as small as possible and that they're as far away as possible. So if we're doing capacitive sensing, one of the best ways to minimize parasitic capacitances is to make sure that everything is integrated on the same chip. So the electronics are integrated on the same chip as the MEMS device itself, so that we don't have to do wire bonding, because the wires that we use to bond from one chip to another are going to be conductors that introduce parasitic capacitances. So monolithic integration is the best thing that we can do. And then we want to make sure that our structures have a large distance between them. So with the surface micromachine structures that we're looking at here, what do you think the biggest parasitic capacitance is, right? So we have a surface micromachine structure. It is literally sitting on top of an electrically conductive substrate. So there's going to be a large bottom plate capacitance effectively that we have to worry about. So we want a trench underneath our microstructure that does not, so that the distance between the substrate and the proof mass portion of our structure is as large as possible. That will minimize that parasitic capacitance. Anyway.
Alongside the circuitry, right? But circuitry is usually two-dimensional.
So it's not, so a surface micromachine structure is integratable with CMOS processes because you can do it effectively on top. So you would do all of your processing for your electronics and stuff like that, and then you would effectively have area on your chip that's dedicated to MEMS devices, and then you would use sacrificial layers to effectively build something on top of that structure. So you wouldn't do bulk micromachining where you're doing like deep chemical etches and all of that kind of stuff because the area of that can eat into your IC area. But surface micromachining is literally, you do sputtering and deposition of thin films, patterning them on top of your pre-existing electronics and all of that kind of stuff to make your microstructure. So that's where these comb drives really come in. In fact, in the development of the ADXL series, the analog devices, accelerometers, they had the circuitry figured out for years before they figured out how to do the microstructure. So they actually have pictures of old chips where it's just all of this interesting VLSI stuff and then a huge blank region for where they were still trying to figure out how to make the microstructure part work. So anyway, all right. So we've talked about parasitic capacitances now as well. Now I'm really done.
So we just want it floating out in space.
Pretty much, yeah. You want it as to be electrically isolated as possible. Or I guess mechanically isolated as possible really would be the way to do it. So that it's not physically near anything else important.
Just have it hooked up to the rest of the circuit with Bluetooth.
Alrighty, so expect a homework on electrostatic sensing sometime here soon. And some of what that is going to be, so I might give you a simple structure and then give you some dimensions, and you have to figure out what direction this thing most easily bends in, which would involve calculating spring constants of guided beams and all that kind of stuff to see if this is, you know, an x-axis accelerometer, y-axis accelerometer, z-axis, and then tell me for a acceleration in that particular direction what the relative change in capacitance is, that kind of. And then I might give you something similar with a plate. So